Hello, welcome today to our channel. We are glad to have you with us. And welcome once again to our series on engineering mechanics. Kindly subscribe, like, share, and leave your comments and suggestions at the comment section. We are continuing our series on engineering mechanics, and today we are looking at the application of equilibrium and structures. Let's look at an example. Good. This is our question for today. In a ship unloading operations, two cables are used to center a car from the ship to its intended position as shown in the diagram below. The support at N is frictionless, only while that in M is a pin support. Determine the tension in the cables and the force in member MN if the automobile weighs 2,000 kilograms. Let's look at how to solve this question. Good. This is our question. And don't forget that we are solving problems on equilibrium together with other theories which you have already learned. In this question also, the first thing we need to do is to draw our free body diagram. Therefore, let's quickly start. Now, looking at this question, we can actually detach this portion from the other systems. We can easily detach this portion from the other systems. And having been able to detach that portion, now let's look at how to draw our free body diagram for the remaining sessions. We know that we are told in the question that from this point M to this point N is a metallic rod. And this N here is a pulley, whereas this support here is a pin. Therefore, it means that from this point to that point, it's a member. And if it is a member, according to the Newton's third law of motion, the force this pin is exerting on this member will point this direction, whereas the force on this pulley, if this is going in this direction, then the one from this pulley is going to move in the opposite direction like that. And since we want to detach this whole vehicle from the other structures, we have been given the weight of this vehicle. So this and that is going to give us the weight of the vehicle, which will now point down like this. Therefore, we can draw the free body diagram for this side of the structure. We can draw the free body diagram for this side of the structure. And the free body diagram is going to look like this. This is our point M. The weight will point downwards like this, W. And we have this cable, which is from M to P. Therefore, the tension in that cable is going to be TMP. And the tension, the force in this member here, the force in this member here, which you have detached or you have cut through at this section, we know that that member is from M to N. Therefore, that is going to give us member force in member MN. And we know that the angle here is 15 degrees. This is 15 degrees. And for this one, we do not know the angle which it makes. Therefore, we can represent that angle with anything, let's say beta. And then from here, we can calculate our weight. We can say that the weight, since we have been given the mass, we are told that the mass is 2,000 kilograms. Therefore, the weight will be equal to 2,000 times 9.81. And from there, W will be equal to 19620 newtons. And since the value is large, you can convert it to kilonewtons, which will be 1.196 19.6 kilonewtons. Then once you have been able to do that, now we need to resolve these two forces here, TMN and TMP, since they are not in the X or the Y to components. Let's pick them one by one. Therefore, resolving TMP into components. Resolving TMP into components. Now, resolving TMP into components, look at it, the direction. This is the starting point of the force, and this is the end point of the force. Therefore, we are going to move up on Y like this. And if we are moving up, we say that it's positive. And then we are going to move this direction on the X. And don't forget that our directions are like this. This side is positive, this side is negative, this side is positive, this side is negative. And so X, you can see that moving in this direction, we are moving at the negative side. Therefore, our X component to be negative. So from here, our S component is going to be Fx equals DMP cos. You can see that the angle beta is facing this, the S component. And if it is facing the S component, if it is facing the, sorry, what we are doing is for TMN, not TMP. Therefore, kindly allow me to erase that and write the right thing. Good. Yes, so we are resolving for TMN. And you can see that now the angle, the S component for TMN, we said that the angle is facing this side. Therefore, the S component is going to be TMN sine beta. And we said that it's going to be negative because it's moving at the negative side of our axis. Negative. And our Y component, we said that it's moving up, so it's going to be positive, but the angle is adjacent to our Y component. Therefore, it's going to be TMN cos beta. TMN cos beta. Now let's resolve TMP also into components. Look at the direction. These are starting point and these are end point. Therefore, if you are resolving that into component, you are going to move this direction on the X, which will be positive. And then we are also going to move up on Y, which will be positive. And from there, our resolution for resolving TMP in resolving TMP now, our S component, we said that is going to be positive, but now our S component, this side is adjacent to our angle. Therefore, it's going to be TMP cos the angle, which is 15 degrees. And then our Y component is also going to be TMP. And now our Y component is facing the angle, therefore it's going to be sine 15 degrees. Good. Then from there, we can write our equilibrium equations. Since the cables are used to center the automobile, therefore it is in equilibrium. And for that matter, we can write our equilibrium equations and say that sum of 4x is equal to 0. And this, when we are moving to the right, it's positive. Therefore, from there, our equation is going to be TMP cos 15 degrees minus TMN sine beta will be equal to 0. Let's call this equation 1. Then we can also write the equilibrium equation for y is equal to 0. And if y is equal to 0, we can say that TMP sine 15 plus TMN cos beta will be equal to 0. And we can call this equation 2. Good. Having been able to resolve that, it means that now we are done with resolving the forces at this side. Therefore, now we can move to the other side and also draw our free body diagram. The first one we drew was for this side, and then the second one should be for this side. Don't forget that we indicated this as going this direction, and therefore we said that this side will be moving this direction. So picking the point N, now we can also draw our nice free body diagram for N. And from N, for N, now we have from N to M moving in this direction. Direction like this. This is MN, TMN. And then we have the force O moving this direction, and it is making an angle of 30 degrees with the horizontal. And then we also have our force Q. So we can call this TNO, and then we can call this TNQ. So TNQ is also making an angle of 20 with the horizontal. Therefore, once you have been able to do this, you can see that now none of the three forces is in the X or in the Y. And therefore, if you get our forces like this, we need to resolve into components. But don't forget that here we said that the angle this is making with the vertical is beta. So if this angle is beta, then from angles, we can also say that because this side and that side is forming a Z angle, then the angle here will also be beta. Therefore, our angle here is also beta. And now we want to resolve all the forces into components. Therefore, let's just pick TNO. We can pick TNO first. But now you realize that from this diagram, this cable is running from point Q all the way to point O. It's a straight cable. Because it's a straight cable and it is on the pulley, they will have the same forces. They will have the same forces. Therefore, we can also refer to TNO as TNO because it is the same cable which is running over the pulley. They are going to have the same force. Good. Good. Or we can just change the name and say that because it's the same cable running from this to that, we can call this also as from. We can actually say that or call it from O to K. From O to K. So we can refer to this as T OK, and then we can also call this as TOK since they will be the same. They will be the same force in the two cables. Good. Therefore, now let's resolve first the one here into component. This one into component first. Resolving this into component TOK, which is making an angle of 20 degrees with the horizontal. You can see that in resolving, this is the starting point, this is the end point of the force. And therefore, we are going to move this direction on the x, and this direction is negative. And so our s component is going to be negative TOK. And you can see that it is adjacent to our angle. The s component is adjacent to our angle. Therefore, we are going to get cos 20. And then our y component, from here, you can also see that we'll be moving upwards. And moving up is going to be positive on y. Therefore, our y component will be equal to TOK sine. The y component is facing the angle sine 20 degrees. Once you have been able to resolve that, now let's come to the next one, which is this one, which is making an angle of 30 with the horizontal. Therefore, TOK, which is making an angle of 30 degrees with the horizontal, is going to be f of x. Now you can see that resolving that is the starting point, this is the end point. Therefore, we are going to move this direction on x, which will be positive, and this direction on y, which will also be positive. However, you see that the s component is adjacent to the angle. The s component is adjacent to the angle, and therefore it's going to be cos. So we are going to get TOK cos 30 degrees, and our y component is going to be TOK sine 30 degrees. Now let's resolve for MN also. Now for MN, this is the starting point, this is the end point, looking at the direction of the arrow. And so we are going to move down on y, which is going to make y negative, and then we move this direction on x, which is going to make x positive. Therefore, resolving for TMN, we are going to get our s component to be equal to, you can see that now our s component is facing the angle. So you are going to get TMN, and because it's facing the angle, it's going to be sine beta. And then our y component is now adjacent to our angle beta. Therefore, our y component is going to be TMN cos beta. And we said that it's coming down. And if it's coming down, our conversion is going to be negative. It's going to be negative. Good. Now, having been able to do this, we can also write equilibrium equations for that portion of our diagram. And let's look at how to write the equilibrium equations for that portion of our diagram. Don't forget that our equilibrium equations are sum of f of x is equal to 0 and sum of f of y is equal to 0. In this case, we are not going to apply our moment because we are dealing with particles. And when we are talking about particles, we don't talk about moments. Good. Let's therefore write our equilibrium equation for the next side. Our equilibrium equation is going to be, we are going to sum all of them are x components. So sum of x is equal to 0. And we are taking movement in the right as positive. Therefore, we are going to get negative TOQ cos 20 plus TOQ cos 30 plus TMN sine beta is equal to 0. And we can call this our equation number 3. And then we can also write our equilibrium equations for the y components. And we are going to take our upward direction as positive. And from there, we are going to get TOQ sine 20 plus TOQ sine 30 minus TMN cos beta is equal to 0. And this will be our equation 4. Good. Now, once you have been able to reach this point, we are far ahead. And the next thing is to be able to solve these equations to get our forces. Therefore, now you can see that we are having 4 unknowns. We are having 4 equations with 4 unknowns. And anytime you have 4 equations with 4 unknowns, it becomes very difficult for you to solve. Even with our calculators, we will not be able to punch it straight on our calculator to get our answers. Therefore, anytime you get 4 equations with 4 unknowns, we can use other deductive methods to be able to solve the problem. How do we go about it? First of all, let us make, because we have 4 equations, now we want to reduce the 4 equations to 2 equations. We want to reduce the 4 equations to 2 equations. Therefore, we are going to reduce our first and our second equations, and then we are going to make TMN cos TMN sine beta and TMN cos beta in our first equations, our first and second equations, the subject. And from there, we substitute them into our third and our fourth equation. So let's see, from equation 1, we find out that TMN sine beta minus TMP cos 15 was equal to 0. So from here, we can say that TMN sine beta will be equal to TMP cos 15. Now we can call this equation 5. And then from equation 2, we also realize that TMP sine 15 plus TMN cos beta minus 19.6 is equal to 0. So from here, we can make TMN cos beta the subject and also substitute to equation 4. Therefore, from there, we are going to get TMN is equal to we are going to get it to be equal to 119.6 minus TMP times 15 times 15, and we can call this equation 4. Equation 6, we can call this equation 6. Therefore, now what we are going to do is to substitute the new equations we are having, which is equation 5 and equation 6, into equation 5, equation 3 and 4, into equation 3 and 4. Quickly, let me erase this side, and then we continue from there. Good. Therefore, from there, we can say that putting equation 5 into equation 4 and equation 6 into equation 6 into equation 4. Now, when we put that into equation, when we put equation 5 into equation 3, sorry, when we put equation 5 into equation 3, we are going to get, because of space, I don't want to write equation 3 again. I'm going to put it straightforward, because we find out that Tm sine beta was equal to that. So I'm going to, wherever I see Tm sine beta, I'm going to insert Tm cos 15. Wherever I see Tm cos beta, sorry for that, Tm cos beta, I'm going to put 19.6 minus Tmp sine 15. Therefore, I'm going to get negative TOQ cos 20 plus TOQ cos 30 plus TMP cos 15 is equal to 0. And if you simplify that, we are going to get negative 0.074 TOQ plus 0.966 TMP is equal to 0. And we can call this now as our equation 7. And then we can also put in equation 6 into equation 4. It is going to give us TOQ sine 20 plus TOQ sine 30 minus whatever we are substituting, which is this, and it's going to be 19.6 minus TMP sine 15. And from here, we are going to get it to be equal to, TOQ sine 20 plus TOQ sine 30 minus 19.6 plus TMP sine 15 is equal to 0. And from there, the simplification is going to be 0. We are going to get 0.842 TOQ plus 0.259 TMP is equal to 19.6, and we can call this equation 8. Now, to get TOKO and TMP, we solve 7 and 8 simultaneously. Therefore, solving equation 7 and 8 simultaneously, we are going to get TOKO as equal to 22.74 kilonewtons, and then we are also going to get TMP to be equal to 1.74 kilonewtons. And once we are done with this, now we have been able to determine 2 out of the 4 unknowns. And therefore, we are left with the 2 other unknowns. We are going to look at how to do that quickly, and then we finish with our question. It's not difficult, it just involves a lot of writing. Allow me to clean this side, even as we solve for the other remaining values, which is the angle theta, and also the value of TMN. Good. Let's continue from there. Now, in order to get our angle, we can also get the ratio of equation 1 and equation 2. We can get a ratio of equation 1 and equation 2. From equation 1, we had equation 5, and from equation 2, we had equation 6. Therefore, we can divide dividing equation 5 by equation 6. Therefore, we are going to get TMP sine beta is equal to TMP cos 15. And we said that we are dividing by equation 6, and equation 6 is, sorry, this one is TMN, not TMP. TMN. And we dividing, we are going to get TMN cos beta is equal to 19.6 minus TMP sine 15. TMP sine 15. But don't forget that we have already calculated TMP from our previous calculations. But here TMN will take away TMN. And this over that is going to give us tan beta. Sine over cos is going to give us tan beta is equal to, and when you simplify, we have TMP and then we have TMP here. So when you put the value of TMP, which we have calculated in our previous calculations, which is 1.74, it's going to leave us with 1.68 over 19.15. And from there, we can see that tan beta, we can see that you just get the beta is equal to the tan inverse of whatever is there, which is 1.68 over 19.15. And from there, beta will be equal to 5 degrees. Beta will be equal to 5 degrees. Then, once you have gotten beta, we can now put beta in any of the equations, equation 1, 2, 3, 4, to get the value of TMN. But I think it's easier we put in equation 1. Therefore, we can say that putting beta equals 5 degrees in equation in equation 5 or 1. 5 was gotten from 1. So equation 5 to get TMN. So we are going to get from equation 5, we had TMN sine beta is equal to TMP cos 15. And we know TMP, we know sine beta. Therefore, we are going to get TMN is equal to TMP is 1.74 times cos 15 all over sine beta, which is sine 5. And from there, TMN will be equal to 19.3 kilonewtons. So that was a bit tedious going through all these equations. And some of you, this might have been your first time of solving a problem with 4 unknowns and with 4 equations. But I hope it is very understandable. Let's go through. If you have any question or any comment, kindly let us know, and we will be very happy to assist you in that regard. Once again, thank you for staying in touch with us, and we ask you to kindly subscribe, like, share, and also hit the notification bell. For now, bye-bye. See you in our next video.